protein folding reaction. Okay, so again, we went from unfolded to, my apologies for my drawings, folded. So we have some concentration of unfolded, some concentration of folded. Assume no intermediates, it has to be in one or the other. And then we said K of folding, so the forward reaction in this case would be product is the folded up protein, reactant is the unfolded, and this is 1 over K unfold. What is the entropy of the folded protein? Zero. How do you know? Because the multiplicity is 1. Perfect. Okay, so here was our equation for entropy, our statistical definition based on multiplicity. Boltzmann's constant times the natural log of 1 is equal to 0. Okay? There is only one way to sort of correctly fold a protein into its native state. What is the entropy of the unfolded protein? What's the sign of it? Some positive number. Okay, entropy is never negative. So it's some positive number. What I would need to know is sort of this piece here, right? How many different, what's my multiplicity? What are the different ways that this thing can be unfolded? And before, we'd sort of said like, oh, there's lots of ways it could be unfolded. Well, it's not infinite number of ways it could be unfolded because literally sterics would prevent some of the possible conformations from existing when it unfolds. So there's some cap on it, and we make some assumptions to decide what that is. Okay? So again, let's look at delta G for the folding reaction would be equal to delta H for the folding reaction minus T times delta S for folding. Okay. Delta S of folding is going to be equal to the product is the folded one, the reactant is the unfolded one. Okay, so this is 0 minus some positive number. Okay. That means this is a negative number, temperature is always a positive number, this whole piece is positive. So we said we expect this to be negative because we know that this happens spontaneously. We know folding is spontaneous in the body. And we're going to measure this with DSC, and we'll talk about it on Monday. Like I said, but when we do calorimetry, our proteins are in a solution. They're in the water, and that enthalpy term is already taking into account the changes that are happening with water inside that vessel. We can't do DSC on some sort of dry, powdered version of protein. I mean, we can, but we don't bother to. That's not what we're interested in for a realistic setting. We could just burn it, but we don't want to. Okay, so how can we calculate S of unfolded? We're going to go ahead and make some assumptions. We're going to use, first of all, I'll tell you, let's go ahead and use the probabilistic definition. Negative n times kb times the sum of I up to n sub c being the number of conformations, the number of ways it can be unfolded is nc. Probability of I times the natural log of the probability of I. Here are the assumptions we're going to make. N is equal to the total number of proteins in my system. N sub c is equal to the number of different conformations of the unfolded state. Okay. It's less than infinity because of sterics. Like I said, it's not infinite. So maybe it unfolds like this. This could be I equals 1, and maybe it looks something like this, and this is I equals 2. This is literally what it looks like in your book. It's just a bunch of different options of squiggles. It draws like 6 or 8 of them. I'm going to quit at 3 up to n sub c conformations. Okay? And the last assumption we make is to let p sub I be equal to 1 over n sub c, essentially meaning that each unfolded state is equally likely and equal energetically. So we're just kind of assuming that unfolded has some energy associated with it, and they all have the same energy when they're unfolded, and they all are sort of, it's equal probability of unfolding in any one of these possible conformations. Okay. It's not realistic, but it's an assumption we make. And then it turns out when you actually do some of this stuff experimentally, the numbers match pretty closely to the assumptions we put on paper to guesstimate. So then if we go up here and we sort of plug our assumptions in to our entropy calculation, S unfolded will be given by negative n kb times the sum from sort of conformation 1 up to the total number of conformations, 1 over n sub c times the natural log, 1 over n sub c. And I am summing this term up n sub c different times. So this is negative n Boltzmann's constant times 1 over number of conformations, the natural log of 1 over the number of conformations, times the number of conformations that there are. Okay. So I'm summing up basically the same probability n sub c times until I've considered all of those unfolded states. This term drops out. And I have negative n kb, the natural log of 1 minus the natural log of the number of conformations. So I just broke that apart. The natural log of 1 is 0. Okay. And so what I have is positive n kb times the natural log. So this negative and this negative just become a positive now when I multiply them together. If I divide both sides by the number of proteins that I have, what I'm basically telling you, and entropy of the unfolded state divided by n is sort of entropy per one protein molecule. Okay? Would be equal to Boltzmann's constant times the natural log of the number of different ways I can be unfolded. If I multiply this whole thing by Avogadro's number, okay, S sub n times Avogadro's number is going to give me molar entropy. I'm just converting number of protein molecules to moles. When I multiply Boltzmann's constant by Avogadro, what am I going to get? R, gas constant, lovely. So now I have molar entropy for the unfolded state is equal to R times the natural log of the number of different ways I can be unfolded. I can draw a little degree sign to indicate standard state, because standard state is 1 molar solution of my protein by definition. Okay. What are the units for this? What are the units for entropy? Joules per Kelvin. What if I see joules per Kelvin mole on the bottom? Do I panic or do I not care? Because I understand that for standard state, it is for 1 mole, okay? Okay, so that's what this slide shows. You'll have all of this both in a scanned copy of this notes. Oh, here's all their drawings. Look how much better their unfurled protein drawings are. Okay, so this goes through the same thing. Molar entropy of the unfolded chain is proportional to the logarithm of the number of conformations of the unfolded protein chain.